So this is my lab 3. The purpose of this lab is to investigate the distance dependence of a magnetic field due to a small bar magnet. I'll then compare the magnetic fields of a magnet on and off axis using the Savart law magnetic fields with simulated ones on GlowScript. As a preview for my findings, the magnitude of the net magnetic field increases as the distance decreases. So using GlowScript, this lab uses fundamental physics principles to model the different magnetic fields, and these principles include, in the computational model, the Savart law is crucial as it relates the magnetic field produced by an object at an observation point to the current that's running through it and the distance. The magnetic field dB for section dl is represented by the formula on the left. When r is much greater than the radius of the loop, so it's far from the loop, the magnitude of the magnetic field has the shape of the on-axis magnetic field of the dipole. You can use those two formulas. And the magnetic dipole moment is I times the loop area, and the direction of the on-axis magnetic field is the same direction as the dipole moment, and this is the same direction as the conventional current I. For the magnitude of a magnetic field of a magnetic dipole on a perpendicular axis, you can use this formula, and the direction of this magnetic field is opposite to the dipole moment. The magnitude of the magnetic field due to a bar magnet is k times r to the n, and this is used to solve for the dipole moment. So in the experimental model, the system is the observation point at the magnetometer, while the surroundings are the bar magnet, which produces the magnetic field as stated in the lab instructions. Initial conditions are that the distance between the magnet and magnetometer is 100 teslas, with the setup shown in the image below. The axes created should be perpendicular here. And in the experimental model, we assume that the magnitude of the magnetic field due to the bar magnet is proportional to some constant times the power of the distance. We also assume that the x-axis is defined by the magnetometer, which points along the width of your phone, and the y-axis points along its height, and the z-axis points out of the screen. So after following the procedure and recording the data, I use this equation to calculate the magnetic dipole moment. And the magnetic field in the y direction could be found by subtracting the Earth's magnetic field from the measured y component at the off-axis point. While the magnetometer is far away from the magnetic field's x component is near zero, and as the distance decreases, the x component increases. So for the computational model, it uses Python and GlowScript to create a theoretical model of the magnetic field. So here are the constants for the model, as well as the function for calculating the magnetic field. And the general formula for the magnetic field of a magnetic dipole is used here. Here's the code for scaling and drawing the errors of the magnetic field of the bar magnet, which includes locations of the arrows and what they represent and the axes. So there's also how to calculate the off-axis magnetic field and the arrows for that on the bottom. So here are the results of the Python code. The magnitude of B from this model is 2.83 times 10 to the negative 5, and the magnitude as per the experimental model was 5.52 times 10 to the negative 5. So the two values are not exactly the same. However, given the various uncertainties and errors in the measurement, the fact that they're accurate to the same order is pretty successful. However, we must acknowledge that there's room for further improvement. So sources of error include that there are other sources of magnetic fields distorting the measurements, like nearby devices or charged objects. There could have also been inconsistent measurements regarding the placement of the phone, the smoothness of the surface, and error within the magnetometer. To further think about the physics concepts in this lab, we can look at the discussion questions. So the results of the Bx and By would have been off by an amount due to the interference by magnetic north, as an intermediate angle would contribute to both the x and y components of the magnetic field. But also note that the z component would have been unaffected since the magnetometer is on a flat surface. Also, since the magnetic field is superposed, this would affect the magnitude of the magnetic field in the second part as well. For the second question, the magnitude of the magnetic field would increase due to the combined magnetic fields of the two magnets. We'd expect it to be about doubled the magnetic field of one magnet due to superposition again, and this can be supported by the previously shown experimental data. And using our formulas from the explanation of principles, the measured distances for each magnetic field would decrease due to the increased magnitude